A seashell can look impossibly precise, like it was shaped with tools instead of grown by an animal. The curve is smooth, the spiral feels intentional, and every turn seems to land exactly where it should. Yet no one is guiding this process, and nothing is correcting mistakes along the way. So how does something alive manage to build a shape that looks mathematically perfect just by growing? That question naturally leads to a bigger one. How do shells spiral so consistently and so cleanly in nature? To answer it, we need to look at how growth, biology, and geometry quietly work together over time, right here, on History of Simple Things. Shells grow through a biological process controlled entirely by the animal inside, usually a mollusk such as a snail or nautilus. The shell is produced by a soft tissue called the mantle, which secretes calcium carbonate along the shell's opening. As the animal grows, new shell material is added only at this edge, never by reshaping older sections. This means the shell expands outward while preserving everything that came before it. Because growth happens gradually and proportionally, the shell curves naturally rather than extending in a straight line. Over time, this consistent edge growth produces a smooth spiral that reflects the animal's changing size rather than any external shaping force. Long before modern science, humans noticed that shells followed remarkably consistent spiral patterns. Ancient Greek thinkers, including Archimedes, studied spiral curves centuries before biology could explain them. Archimedes described geometric spirals as abstract mathematical forms without knowing that similar shapes were growing naturally in shells. During later scientific periods, scholars began comparing these mathematical spirals to natural objects, including shells, horns, and plants. This comparison revealed that shell growth followed predictable geometric rules rather than randomness. It marked an early moment when nature and mathematics were understood as connected systems, showing that organic forms could emerge from simple, repeatable principles. The spiral shape found in many shells closely resembles a logarithmic spiral, a curve that expands while keeping the same proportions at every scale. In this type of spiral, each new turn is a slightly larger version of the previous one, creating visual continuity. This happens because shells grow by a constant percentage rather than a fixed amount. Each new layer increases size without altering the overall shape. This self-similar growth explains why shells remain recognizable at any stage of life, from juvenile to adult. It also explains why broken shells still resemble complete ones, since every section follows the same underlying geometry. Genetics plays a major role in determining how a shell spirals. The direction of the coil, whether it turns left or right, is genetically determined early in development. Most snails coil to the right, while some rare species coil left due to differences in cellular division patterns. Genes also influence how tightly the shell coils, how tall it grows, and how quickly it expands outward. These inherited instructions guide how the mantle deposits material along the shell edge. Over evolutionary time, small genetic changes can lead to noticeable differences in shell shape between species, while still preserving the same basic spiral principle. Spiral growth is not only visually consistent, but also structurally efficient. A spiral allows a shell to increase in size without sacrificing strength or stability as the animal grows. Curved surfaces distribute stress more evenly than flat ones, helping prevent cracks that could form under pressure from waves, impacts, or predators. This efficiency means the animal gains more internal space without needing thicker or heavier material, which would require more energy to produce. From an evolutionary perspective, shells that offered strong protection while using minimal resources gave their occupants a clear survival advantage. Over millions of years, this made spiral growth a naturally favored solution among many shelled organisms across a wide range of environments. Shell spirals are often associated with the golden ratio, but this idea is frequently overstated. While some shells roughly resemble Fibonacci-like proportions, most do not follow the golden ratio precisely when measured. Instead, shells form logarithmic spirals shaped by biological growth rates, physical constraints, and genetic variation rather than fixed mathematical constants. Nature prioritizes flexibility and function over numerical perfection, allowing growth to adapt to changing conditions. This distinction matters because it shows that shells are not aiming for an ideal number, but responding to real-world demands placed on the organism. The result is a reliable spiral pattern that allows variation while preserving overall structural coherence. Shells spiral perfectly because they grow in a consistent, proportional way over time. As mollusks add new material only at the shell's edge, their homes expand outward without changing shape, naturally forming spirals that follow simple geometric rules. Genetics controls the direction and tightness of the coil, while physics and evolution favor shapes that are strong, efficient, and dependable in the real world. What looks like careful design is really the outcome of steady growth, repeating the same rules again and again without adjustment or correction. Each shell becomes a visible record of how life grows, adapts, and preserves structure through time, showing how complex patterns can emerge from simple processes carried out patiently over a lifetime. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.